Hi, over on my screen you can see a demo of twoway. Twoway is an open source Go package that we have developed at Confident Security. It uses hybrid public key encryption, or HPKE for short, to encrypt request and response messages. Essentially, this means that twoway guarantees the integrity of a round trip between a sender and a receiver, or a client and a server, which is, as you can see, the terminology that we'll be using in this demo. But let's just start at the top and go from there. The first thing you'll see is that we're setting up this suit. This is a HPKE suit. It's essentially a selection of algorithms that HPKE should use. If you're unfamiliar with HPKE, it's a standard that combines symmetric and asymmetric key encryption to achieve a performant crypto system. Like I said, as a user of twoway, I don't know if I actually said that. Maybe it was a different tech. But the important thing is that you provide the same suit to both the server and the client. If those suits don't match, then you'll have a hard time using twoway because, decryption will fail of the messages that you're sending because, you're using a different algorithm. The next thing you'll see is this shouting echo handler, which is something we'll be using for this demo. It takes an input IO reader, reads everything that's in there, capitalizes the result, and returns that as an IO reader again. This is quite central to how twoway works. All data is being passed around as IO readers. We'll see more of that in a bit. Then we set up the server and the client. In this example, we're just passing in the server directly and calling methods on it. In reality, there will likely be a network connection or any kind of transport between the client and the server. Twoway doesn't care about it. It just deals with IO readers. You can see that we're constructing a plaintext request message, passing that as an IO reader to the client. Then the client returns an IO reader as plain text. We read everything and we print it out. Let's just see if that actually works before we continue, which would be fun if it didn't work, but no, it does work, which is great. Love it. As you can see, we put in a lowercase text and get a uppercase text in response. Nice. Let's begin then by looking at the client, because we haven't actually even seen twoway yet. So the first thing we'll see here is that the client takes the public key of the server and constructs a so-called request sender. Now in this demo we're showing the one-to-one flow, where a single client talks to a single sender is communicating with a single receiver. This sender requires the public key of the receiver. In addition, it also needs a single byte ID of the key. This is due to twoway supporting OHTTP, or being compatible with OHTTP, which encodes this as part of the well, it doesn't encode it, it uses it as additional data during encryption. But anyway, if you're not using key IDs, just pass a 0 byte and you should be fine. You'll also see that we're passing in the suit, as mentioned before, the public key itself, and a random reader, which is required by HPKE to construct a shared secret between sender and receiver. That's all there is to setting up the client. The magic really happens in this round trip method, where you will see that we're using the sender that we set up before to create a so-called request sealer. This is a type that also implements IO reader, as you can see here. This sealed request contain return, if you read from it, it will return the ciphertext of the plain text. In other words, this contains, if you read from here, you get the encrypted bytes. That's what I'm trying to say. We then call the serve request function on the server to handle the request. We also pass around these media types. I might discuss those later. As a user, you need to know that they need to match. So whatever media type you're using with the sealer, you will also need to use it on the receiver side, as we'll see in a bit. Then the server returns a sealed response and a media type. Again, these media types will need to match. And then we use not the sender, but the sealed request to construct a so-called response opener. Whereas the sealer is the one that does the encrypting, the opener is the one that does the decrypting. So in this case, we're passing in the sealed response, constructing an opener that will again return an IO reader, which will then be returned. As you can see, it's an IO reader since it's discompiled. Let's look at the serve request function. I think this should all be clear. Oh yeah, sorry. Let's discuss this. So we're not calling new response opener on sender. Why? Well, essentially, each request that you begin sealing starts a new session from the perspective of the sender, a new round trip. So you seal one request, then you get a response in return, but that response is tied to the original sealed request. So instead of creating a response opener from the sender, we're creating it directly from the sealed request. Because next to being an IO reader, this also contains more context. It contains the so-called encryption context, or HPKE sender context. With that said, we'll see a very similar pattern on the server. So let's first quickly go over how we set up the server. We pass in a suit, generate a random public key and a random private key, and then set up a request receiver. This is similar to the request sender that we saw earlier, except it isn't tied to any particular sender. So this receiver can receive requests from multiple request senders. We pass in the suit, again, the key ID for OHTTP compatibility, the private key, and again a random reader, which is required for it's an internal detail of the way two-way works, but it's required for the nonces. I'm actually not sure from the top of my head if it's for two-way or for HPKE, but let's skip over that. It requires a random reader. So here we call we go back to the serve request function, which receives the sealed request from the client from here. So we create a request sealer, which is an IO reader. In reality, we might be passing this over via a TCP connection or a HTTP request or whatever. Here we're just passing it directly as an IO reader. And we also need to know the media type. So we use we create a request opener using the receiver. We pass in the sealed request, the media type, and we again get back a IO reader, which if you read from it, you will get the plain text request, which we just pass the full reader to the handler, which we saw earlier, which does the capitalizing, and then we get a plain response reader, plain text response reader. We then, in a similar pattern that we saw on the client, we use the request opener to construct a response sealer. This is because, again, just like there was a cryptographic context on the client, there's also a cryptographic context on the server, which is tied to the original request, which is why you need to create a response sealer via the request opener and not via the receiver. So here we create a response sealer, again with a media type, and return it. Again, IO reader, as we saw here, as we saw here, and that's all there is to it, essentially, to using two-way.